Greetings. Steam power plants are key elements to electric power generation. In combination with gas turbines, which we introduced in previous videos, and hydroelectric power plants, they produce most of the electricity that we use. Of course, today, renewable energies and wind power plants have come to generate more energy. But I think steam power plants will be with us for a long time. Now, I'll tell you what they are about. They work on a very simple cycle which is called Rankine cycle. If you remember, I told you that when we have a Brayton cycle, which was the cycle for gas turbines, we had two constant pressure lines, which was P1 and P2. And what we did was to say that the work gained from expanding hot medium is more than the work required for compressing a cold medium. So what we do, we get some cold, say, air from point 1, compress it to point 2, then heat it to point 3, and expand it to point 4. And simply because constant pressure lines diverge and the vertical distance between them increases with temperature, then the work gained from expanding hot air or hot combustion products would be larger than the work required to compress cold air. And the net result would be some work that could be used for running a generator and producing electricity. Now, as we calculated before, this work in the compressor could take as much as half the work produced in the turbine. So it's a large share. And steam turbines use this drawback, in fact, to do something else. What do they do? If this is the TS diagram and this is the saturation dome, and these are two constant pressure lines, say this is one and this is the other. Okay, gas turbines work in very, very high temperatures. They work somewhere here. But what the steam turbines do, compress liquid and then expand the vapor. So the steam turbines, what they do, they compress liquid, they expand vapor. What's the benefit of it? You see, if we denote these points with 1, 2, 3, 4, this is the control volume, and this control volume um, work is done, and assume that it is adiabatic and it is reversible. So the adiabatic reversible work of a control volume of a control volume is work equals minus integral VdP. Now, what's the advantage? The specific volume of the liquid is far smaller than the specific volume of the vapor. And the outcome is that the work that is gained from expanding between the same pressure lines would be far larger than the work required in compressing these two between these two lines. I haven't really drawn this curve well because these lines are almost sticking to um, the saturated liquid line, and they are very close, and this line is very, very small in reality. And the cycle which does this job is called Rankine cycle. The cycle is called Rankine cycle. This is the Rankine cycle, and this is the basic cycle for steam turbines and the steam cycles. Okay, now, as an example, just to show the work of a standard steam cycle and a Rankine cycle, we just select one problem where pressure here is 0.01 megapascals and the pressure here is 10 megapascals. And the temperature where steam enters the turbine is 800 degrees C. So this would be our cycle. Why did we denote these values as key values? These are not selected just randomly. They are selected for a purpose. You see, the different instruments that bring about this cycle are four. The basics are four. This work is done in a pump. This work is done in a pump. So saturated water at point 1, saturated liquid water at point 1 is taken and compressed to a higher pressure to pressure at point 2 in a pump. Then it is delivered to another instrument, which is called a boiler. This is the boiler, which just heats that water to values as high as 800 degrees C. Just to give an idea of what that means, this temperature is critical point temperature is 374, about 374 degrees C. 800 degrees C is a bit high, is a bit unusual for steam turbines. The usual value for steam turbines is about 500 to 600 degrees C. But still, this is an example, and it's good to have values, different values with higher values. Now, this hot steam, where its pressure is high and its temperature is high, expands in a turbine. And once it's expanded in a turbine, it comes out at some point, and then as the second law told us, it has to deliver some heat to the colder reservoir. And that is done in a part which is called a condenser. A condenser, where in fact this steam condenses and returns to this. Unlike gas turbines, where they were generally open cycles, and they couldn't be closed cycles because air in them would mix with the fuel and it would burn and it would lose its oxygen. So it couldn't be recycled inside this system. For gas turbine, for steam power plants, they are closed cycles, and it is water which is compressed, is heated, expanded, cooled, and the heating happens outside. I mean, the water doesn't mix with anything, just to heat up, not like air in a gas turbine. Here, the combustion happens outside water, away from water, in the boiler, and the heat released from the combustion, which it happens in some air, or it's just the exhaust gases of a gas turbine, that combustion products would come and heat this water to 800 degrees C. Now, if we draw a diagram for this cycle, the diagram would be a pump, would be a pump which receives water from point 1 and delivers high pressure water to point 2. And then it delivers it into a boiler. This is our boiler, which heats it to point 3, and then it goes to a turbine, which produces electricity, and the outcome would come to a system called a condenser, where the steam, a lot often saturated steam, and with some high quality steam. In fact, a lot of times this line lands just inside the saturation dome, and then it comes to a condenser. This is the boiler, this is the pump, this is the condenser, and the outcome would return to point 1, and this is point 4. And well, and this is our cycle. Usually, this pump is supplied from the electricity generated from this in this turbine and this generator. So it's not usually there is no direct contact between this turbine and this pump, unlike what is quite common in gas turbines, with this turbine directly runs this compressor, but in steam power plants that's not the case. Now, when we work with cycles, it's a very good job to draw a table and in that table specify different points of the cycle and their key properties. Now, in order to find all properties, what we do need is the steam table. And the wattage properties on the steam tables, I have just selected 3 lines. These two are for this problem, and this one I shall use in my next problem when I add reheat to the steam cycle, to the Rankine cycle. But what I need for this problem are to know for any pressure is the saturation temperature. Vf, we need it. I shall tell you why. And then it is enthalpies and it is entropies. These are water properties that I have to use to know where in the table we are and where in the diagram we are. So these are water properties. These are relevant water properties. Of course, I shall use other properties if I go to um, superheat conditions, but these are saturation properties that I shall use just to feel that table that I drew. Now, let's see what do we have in this table and what we don't have. For point 1, we know that the pressure is 10 kilopascals. For point 1, because it is 0.01 megapascals and therefore point 0.1 is 10 kilopascals. Its temperature is the saturation temperature, and the saturation temperature for point 0.1 is 45.81 degrees C. And we have other properties for it. We know that H is HF, which perhaps is a good job if I keep this underneath and you see where I'm taking my numbers from. H is 191.81 and S is 0.6492. 0.6492, and that is all properties for point 1. Now, for point 2, we don't know much. All we know is that the pressure is 10,000 kilopascals, 10 megapascals. We don't know its temperature. We have to calculate that. We don't know its enthalpy. And for the ideal cycle, we know its entropy, and that would be the same as 1, which is 0.6492. 0.6492. Now, these are points 1 and 2. As for point 3, we know its pressure. It is 10,000. It is 10,000 kilopascals. We know its temperature. It's 800 degrees C. And since its temperature is larger than saturation temperature for 10,000 kilopascal, you see for 10,000 kilopascal, saturation temperature is 311 degrees C. So since its temperature is larger, then it is in a superheat condition, and we have to go to the superheat table, and from that table we would calculate it, we would read it in fact to be 14.8, that is the enthalpy, 4.3, and entropy is 7.4085 kilojoules per kilograms Kelvin. As for point 4, we know that the pressure is 10 kilopascals. The temperature we don't know yet. If this point is inside the um, saturation dome, then the temperature is clear. But if it's not, then we have to calculate it. So we don't know the temperature, we don't know therefore the enthalpy, but we know that for the ideal Rankine cycle, process 3,4 is isentropic, and therefore it is 7.4085 kilojoules per kilograms Kelvin. And we now have to calculate the rest of these properties to fill in this table. Well, we did find properties as much as we could. Now, what we need to do is to simplify equations before we could do any calculations for any of the pump, boiler, turbine, or condenser. And the equations we have had plenty of practice up until now for calculating individual items, but still I have to review and set up the equations that I want to use. All these systems are control volumes, they are steady state. So the left-hand side of these equations, these left-hand sides would vanish all. For the basic Rankine cycle, um, we ignore changes in velocity or elevation, and the basic Rankine cycle is reversible, or perhaps we would at some stage account for irreversibilities, but at the same time, we know how to do that. For example, for a turbine, we know how to calculate turbine efficiency, and we shall do such practice shortly when we are doing the reheat steam turbine or reheat Rankine cycle. But anyway, it is the heat transfer is usually turbine is 0, but the heat transfer in boiler and condenser is present. In the boiler and condenser, the work is 0, but the pump and the turbine heat transfer is 0. So a very simple version of these equations would be 0 equals m dot I minus m dot E, and select whichever item you want, boiler, turbine, condenser, or pump, and then for whatever you want, say if you want a pump, just the inlet is 1 and the exit is 2. So that would be easy just to implement it to any of these elements. For the first law of thermodynamics, 0 equals Hi minus He plus Q minus W, where uh, for uh, for boiler and condenser, Q has values, boiler and condenser. Q has value and W is 0. And for pump and turbine, for pump and turbine, has value and Q is 0. So I could write it here for boiler and condenser. Q has value, but W is 0, and for pump and turbine, Q is 0, but W has value. So this is what how we simplify this equation. And the second law of thermodynamics, as we said, 0 equals Si minus Se plus Q over Tb and plus S dot gen, where S dot gen is 0. I would just extend it here. S dot gen is 0. S dot gen equals 0. In fact, it is S dot gen over M dot because I'm just dividing everything by M dot. So S dot gen is over M dot is 0 for reversible processes. Reversible processes. And Q equals, which for the basic cycle, all processes are reversible, and Q equals 0 again for pump and turbine, for pump and turbine. So this is how we simplify everything. In addition to that, this is a very useful equation for calculating the pump. So this equation is very useful for pump. And this is what we have for our calculation. This is the general scenario that we have for our calculation. Now we start with the pump, and we know that for the pump, W equals minus integral VdP. And we know that the specific volume for point 1 is 0.00101. So pump work would be for the pump, for pump, W pump equals, and from the first law, we could also write it as H1 minus H2, and that equals minus, it is, we usually assume V to be constant because it is compressed liquid and V doesn't change that much. So it is minus 0.00101 times 10,000 minus 10 in terms of kilopascals, and the outcome for WP would be 10.09 kilojoules per kilogram. This is how we calculate the work of the pump. Now that we know the work of the pump, we also know H for point 1. You see, H for point 1 is known, and so we could insert it into this equation and calculate H for point 2. H2 equals H1 H2 equals H1, and there's a minus here, which we shan't forget because we have to do work. H2, it goes to the other side, and this work comes to this side, so it is H1 plus uh, pump work is equals, and I have actually applied this minus here, so it would be 191.81 plus 10.09, and that equals 201.9 kilojoules per kilograms, and that is our enthalpy for point 2. Let's write it here, 201.9. Now, once we have the enthalpy for point 2, the best way to find other properties, which is basically its temperature, is to see this enthalpy corresponds with which saturation enthalpy for which saturation temperature. And just trying a few values, the value that we would get is T2 equals 48.2 degrees C. So I will write it also here. This is 48.2 degrees C. So now we know 3 of the key points in our cycle. The only point left is point 4. The only point left is point 4. And the key property that we have is the process is isentropic. It is the turbine has no heat transfer, and it is reversible. So Si and Se would equal for the turbine. And what we write it is that for the turbine, Q equals 0 and S dot gen over M dot also equals 0. And the conclusion is that Si equals Se. And therefore, what we know for point 4 is that P4 equals 10 kilopascals and S4 is 7.4085 kilojoule per kilogram Kelvin. Now, let's refer to our table and see for 10 kilopascals, Sg is 8.14, which is larger than this value. And now we find out that our drawing wasn't very good. We have to redraw our cycle just to show that where point 4 is. Now, let's redraw our cycle, and the cycle would be, this is a TS diagram. This is the saturation dome. This time what I would do, I would draw the lines. This is the 10 kilopascal line, 10 kilopascal line, and this is the 10 megapascal line. Just remember that this point is 373 degrees C about, and it is 22 megapascals. So we know where we are. And if, say, this is 800, which is, of course, not to scale, but because this line is has to have a very sharper slope, but still, we just try to draw it higher than 373, so it is 800 degrees C. And if I draw the constant entropy line, it would end up somewhere inside the saturation dome. So this would be point 4, this would be point 3. And as for point 1 and 2, I will try to draw it, the pressure line, more similar to what they are, and they are very close. This is point 1, and this is point 2. This is a better diagram, is a more representative diagram than what I had drawn before. Now, since entropy is the same, we know the entropy for point 4, and therefore we can calculate x4. X4 is 7.4085, which is the entropy for point 4, minus S1, which is 0.6492, and divided by SFG, which is 7.4996, and the outcome would give us X to be 0.901. This is our quality, and what we can do now is to calculate H4. H4 equals HF plus X HFG. We have all the values. HF is 191.81 plus 0.901 times HFG, which is 2392.1, and the outcome for H4 is 2347, 2347.8 kilojoule per kilogram. And now we can fill in this table, which is the temperature. Now is the saturation temperature, which is 45.81. The quality is 0.901. We know also the quality, and H for it is 2347, is 2347.8 kilojoule per kilogram. And this basically fills our table. I have kept a few extra lines. I would fill them in my next problem. But this problem, at least for this problem, we have all the points for the cycle. You see, this is a fairly standard procedure, and of course, a real cycle would have efficiencies and would have more points, but it's fairly the same. For point 4, you have to be able to do a calculation similar to this. Of course, if there is efficiency, your calculation would be slightly more different. We have had plenty of those examples when we were talking about the second law of thermodynamics. But as it is, you have to calculate all the all the 4 points, and then we are in a good position to calculate the cycle properties, that is, work, heat transfer, and efficiency. The next step is calculating turbine work. And using this equation, there is no heat transfer for the turbine, there is work, and it's the difference between inlet and exit enthalpies. So what we do is turbine work is H3 minus H4, and that equals 4114.8 minus 2347.8, and this would be 1767 kilojoule per kilogram. And if this is supposed to be a 200 megawatt power plant, if P is supposed to be 200 megawatts, then the mass flow of water required for this power plant is 200 times 1000 and divided by 1767, and that would be 113.836 kilogram per second. That's a large, large value for mass flow rate, and this is why steam power plants are usually used in places, are usually installed in places where there is plenty of water. Not only that they need such water for their condensers, but even the water required for the cycle itself is quite a large value. Okay. Now, heat transfer Q equals, this is for the boiler, this is for the boiler, and it is H3 minus H2, and that would be 4114.8 minus 201.9, and QB would be 3912.9 kilojoule per kilogram. And the efficiency of this cycle, the efficiency of the cycle would be what we have gained, which is the work from the turbine minus the work used by the pump, which is of course small, but let's calculate it divided by Q, and this would be 1767 minus plus 10.09. Sorry, this should be a minus because this work is deducted, divided by 3912.9 kilojoule per kilogram. And the efficiency of this cycle is 44.9%. This ratio is 0.449. Well, now we have this efficiency. Let's compare it, just like what we did before with the efficiency of a Carnot cycle. You see, the simple Carnot cycle, we could assume two Carnot cycles for this problem. One would be a Carnot cycle, which is between these lines. And the other would be a Carnot cycle, which is between these lines, depending if you assume the hot temperature for this cycle as 800 or if you assume it to be T11, which is the saturation temperature for the saturation temperature for 10 megapascals. And we would get two values. For this smaller cycle, the Carnot efficiency is eta equals 1 minus 45.81 plus 273.15 and divided by 311 plus 273.15, and that is 45.4%, 0.454, which is not that different from what we have gained. But look, we've been adding heat at far higher temperatures. So this is a very optimistic evaluation and unrealistic. The other extreme is if we assume that we calculate it for this larger cycle, and the efficiency for that is 70.3%. So we have two extremes for the ideal Carnot cycle, 70% or 45%. And the reality is 44.9%. Well, this was our problem for the simple, very basic Rankine cycle, steam turbine cycle, but Rankine cycle has many alternatives, and I will try to show you and calculate for you a few of them in my next videos. Cheers!